This is Dr. Shankaraiah from Department of Physics. So, in today's presentation, I am going to discuss about Module 3, which is lasers and fiber optics. In this, I will cover the second part of lasers and fiber optics, which is fiber optics. So, the topic is principle and construction of optical fiber. So fiber optics started in 1870 by John Tyndall, and it was company who coined the term fiber optics. By 1960, it had been established that light could be guided by a glass fiber. So this fiber optics or optical fiber that was first started in 1870 by John Tyndall, and the person who first named it is Kapani. Named it as fiber optics. So after around 100 years, 1870 to 1960, after around 100 years, it has been established that we can use the optical fibers to send information, and we can use the optical fibers in communication. Okay. So fiber optics is a technology in which signals are converted from electrical into optical signals and transmitted through a thin glass fiber and reconverted into electrical signals. So it's a technology, fiber optics is a technology in which signals are converted from electrical into optical signals. Okay. And these optical signals are transmitted through a thin glass fiber and reconverted into electrical signal. We will discuss about communication diagram where we will discuss the total different parts of this communication system and how we use the optical fiber in communication system. So the first point here is that how do we use optical fibers in communication, right? So in we use optical fibers to transfer light signals. So only light signals are propagated through optical fiber. So but whatever data we have, whether it can be audio signal or video signal, the signal will be in a electrical signal. Okay. So the first audio or video signal which is in the form of electrical signal will be converted into optical signal. Okay. The audio or video signal which is in the form of electrical signal will be first converted into optical signal using some electrical components. We will discuss that in communication diagram. And then once we have this light signal or optical signal, this signal will be transmitted through a fiber. And once we reach, okay, so basically, so you have a fiber. So let us say this is a fiber. Okay, this is the fiber. I have the fiber, and whatever audio or video, whatever signal I have, audio signal or video signal, this signal will be converted. First, it will be in the form of electrical signal. This electrical signal will be converted into optical signal using some electrical components. Okay. So once we connect these, convert the signal from electrical to light signal, that signal will be given as input. Okay. So this is some component that converts electrical signal to light signal, and then once we have this light signal or optical signal, this signal will be given as input to the optical fiber that will be propagated through the fiber. The light signal will be propagated through that fiber, and we will receive the output. We will receive the light signal as the output. Okay. And this output signal, okay, so input light signal and output also light signal. So this output light signal will be again converted into electrical signal. Okay. So that will be converted again into audio or video signal which you have given as input. Okay. So this is how we use optical fiber in communication system. Okay. So looking at its diameter, so it is very thin. Optical fiber is very thin as human hair, around 70 micrometers or 0.003 inch diameter. So very thin. So how do we define optical fiber? An optical fiber is a cylindrical waveguide made of transparent dielectric. It can be either glass or clear plastic, which guides light waves along its length by total internal reflection. Okay. So optical fiber is nothing but a waveguide, cylindrical waveguide. So you have it is in the form of a cylinder. It's a cylinder. Cylindrical waveguide. Waveguide is nothing but the medium that can transmit light. Okay, what is a waveguide? Waveguide is a medium in which light signal can propagate. That is why we are saying optical fiber carries only light signal. So that is the reason why we are saying optical fiber is a cylindrical waveguide. It is a waveguide. It's a medium way light signals can propagate, and it is in the form of a cylinder. So it is a cylindrical waveguide. And what is the material that is used to fabricate this? It is made up of dielectric material. The dielectric you can take it as glass or a plastic. So we are fabricating this optical fiber using glass or plastic, which comes under dielectric. Okay, so optical fiber is a cylindrical waveguide, and it is made up of dielectric material. Dielectric material, you can take it as a glass or clear plastic, and this optical fiber is going to guide light waves along its path by total internal reflection. Right? So optical fiber is nothing but it is in the form of a cylinder, and it is actually made up of dielectric material. So you can use glass material, or you can use plastic to fabricate this optical fiber in the form of a cylinder. But this is a waveguide. Optical fiber is a waveguide because we are saying this as a waveguide because it is a medium which guides the light waves. Okay? And the light in this optical fiber can propagate through total internal reflection. It can propagate through the fiber by total internal reflection. Okay, so optical fiber guides the light waves. It guides the light waves along its length by total internal reflection. Okay, so this is the phenomenon that is used in optical fibers for the propagation of light signal. Okay, let us see its construction, and now we know the principle for the propagation of light in optical fiber. So the principle for the propagation of light in optical fiber is total internal reflection. Principle. So the principle for the propagation of light is total internal reflection. Okay. So, and we have defined optical fiber. What is optical fiber? We have defined it. It is a cylindrical waveguide, and it is made up of dielectric material, and it guides the light waves through total internal reflection. Next, so in detail, the principle for the propagation of light. The propagation of light in an optical fiber from one of its ends to the other end is based on the principle of total internal reflection. Right. So the light propagates in optical fiber based on the principle of total internal reflection. When light enters one end of the fiber, so optical fiber is a cylindrical waveguide. So when light enters from one end of the fiber, it undergoes successive total internal reflection. Okay, so it undergoes successive total internal reflections from side walls and travels down the length of the fiber along a zigzag path. Okay, so a small fraction of light may escape. A very small fraction of light may escape through side walls, but a major fraction emerges out from the exit end of the fiber. Light can travel through fiber even it is bent. Even you bend this optical fiber, so for example, I have bent this. There is, because of some reasons, the fiber is bent. Even if the fiber is bent, the light signal can propagate through this optical fiber. So we have learned that the principle for the propagation of light in optical fiber is total internal reflection. Okay, when we give the light as input signal from one end of the fiber, it undergoes successive total internal reflection at the side walls of this optical fiber, and a very small fraction of light may escape from the side walls, but major fraction of the light will be received at the output end. And light can propagate through this fiber even there is a small bend of this fiber. So that is the principle for the propagation of light, and we will discuss in detail when does this total internal reflection occurs. What is the angle? What is the incident angle? So that the light that enters into the optical fiber undergoes total internal reflection. Okay, so that we'll discuss in detail in the coming slides. So now I am going to discuss about the construction or structure of optical fiber. So what is the construction of optical fiber? So what are the different parts of optical fiber? Okay, so we can clearly see this is the optical fiber, and this is in the form of cylinder, and there are three layers of this cylindrical shape. Three, uh, three cylindrical shapes. These are spherical shapes. You can see the first one is the innermost spherical shape is a core. The innermost one is a core. Okay, the innermost cylinder is a core, and the next to the innermost is cladding, and the outermost layer is called buffer or jacket or sheath. Basically, it protects the fiber from the environmental damages or contaminants. So there are three layers in optical fibers. The innermost one is core, and the next to the innermost is cladding, and the last outermost one is called jacket or buffer. Okay, so these are the three spherical regions. The diameter of the core is around 8 micrometers to 62.5 micrometers. Okay, so the core diameter I am talking about, the core diameter is around 6 micrometers to 8 micrometers to 62.5 micrometers. Okay, and coming to the cladding diameter. So this is next to the core, we have cladding, and the cladding diameter is around 125 micrometers. And the outermost is jacket, and its diameter is around 250 micrometers to 900 micrometers. Okay. So you can clearly see, even if there is a bent of this optical fiber, the light can undergo propagate through this optical fiber through total internal reflection. Okay, so this is a pictorial representation of the structure of the optical fiber. The details are given in the next slides. Okay, so a practical optical fiber is cylindrical in shape and has in general three coaxial regions. So the innermost cylindrical region is the light guiding region known as the core. In general, the diameter of the core is around 8.5 micrometers, 8.5 millimeter. Sorry, this is a micrometer. So 8.5 micrometers to 62.5 micrometers. It is surrounded by a coaxial middle region known as the cladding. The diameter of the cladding is around 125 micrometers. The refractive index of the cladding, we are denoting the refractive index of the cladding as N2, is always lower than the refractive index of the core. So the refractive index of the core, okay, refractive index is index of core. Refractive index of core is N1, and refractive index of cladding is N2. And we know that the refractive index of core is always greater than the refractive index of cladding. Okay, so the refractive index of core is always greater than the refractive index of cladding, or other way you can say the refractive index of cladding is lower than the refractive index of the core. Okay, so we need these refractive index in this relation because we want the light to undergo total internal reflection. So light launched into the core and striking the core cladding bound interface at an angle greater than the critical angle will be reflected back into the core. Okay, so once we launch the light into the core and that striking the core cladding interface at an angle greater than the critical angle, So the angle of incidence theta I must be greater than a critical angle. We don't know what is this critical angle, but it's clear that when the angle of incidence theta I is greater than this critical angle, only then the light will be reflected back into the core and there will be total internal reflection for this light. Okay, so this is the angle of incidence and reflection are equal. Light will be continue to rebound and propagate down to the fiber. Once light undergoes total internal reflection, then there will be continuous total internal reflection throughout this fiber because the angle of incidence and angle of reflection will be equal. The outermost region is called sheath or a protective buffer coating. It is a plastic coating given to the cladding for extra protection. This coating is applied during the manufacturing process to provide physical and environmental protection for the fiber. Okay. So one important point is that we will find the light undergoing total internal reflection only when the theta I, the angle of incidence, is greater than the critical angle. Only then there will be total internal reflection. And the outermost layer of this optical fiber is important because it is going to protect the fiber from the physical and environmental damages. Okay. So the buffer is elastic in nature and prevents abrasions. The coating can vary in size from 200 micrometers to 900 micrometers. So this is just the outermost layer or coating to protect the fiber. Okay. So to sum up the construction of optical fiber, so this is the construction of optical fiber. So to sum up the construction of optical fiber, core is the innermost light carrying member. Core is the innermost light carrying member. This is the innermost cylinder is the core. So this is the core. And the cladding is the middle layer. So this one is cladding. So this one is, second one is the cladding, which serves to confine the light to the core. So the cladding is very important because it is going to serve the light. It is going to confine the light to the core. That is the reason why cladding is very important. Buffer coating surrounds the cladding, which protects the fiber from physical and environmental effects. Okay. So this is a summary of the construction of optical fiber. Okay. So the question is that what is the importance of cladding? Okay. So the cladding performs the following important functions: keeps the size of the fiber constant and reduces loss of light from the core into the surrounding air. The first point is that cladding is going to keep the size of the fiber constant. Okay. And it reduces the loss of light that is going to escape from the optical fiber. Very important advantages. And it protects the fiber from physical damage and absorbing surface contaminants. Because of the sheath, because of the cladding, it is going to protect the fiber from physical damage and from absorbing the surface contaminants. It's also very important. And the third one is reduces cone of acceptance and increases the rate of transmission of data. Okay. It reduces the cone of acceptance and increases the rate of transmission of data. Because of the cladding, the rate of transmission of data in this optical fiber is more. And we will see what is this cone of acceptance. We will discuss about this acceptance angle and cone of acceptance in detail in the coming presentations. A solid cladding instead of air also makes it easier to add other protective layers over the fiber. Instead of taking air as a cladding, you can make a solid cladding, which will make it easier to protect to add other protective layers for this fiber. Okay, so these are some advantages or functions of the cladding we have discussed. So we have completed the structure or structure of optical fiber, construction or structure of optical fiber. This is a small point to discuss about how we are going to use or what are the parts that are there in the communication system, in optical fiber communication system. Okay, so an optical fiber is used to transmit light signal over long distances. It is essentially a light transmitting medium, its role being very much similar to a coaxial cable or waveguide used in microwave communication. Okay, so yeah, so optical fiber requires light source and for launching light into the fiber at its input end and a photo detector to receive light at its output end. As the diameter of the fiber is very small, the light source has to be dimensionally compatible with the fiber core. Very good. So earlier we used to have microwaves in communications, but now we are going to replace. We have replaced the microwaves using by these optical fibers, where we transmit the light signals over long distances, right? So optical fiber requires a light source. So we are going to launch the light into the optical fiber. So this is a cylindrical optical fiber where we need to launch the light signal, whatever signal we have, audio or video signal, that is converted from electrical to light signal, and that signal must be launched into the fiber. So we need a light source, the source that can be launched the light into the optical fiber input end, and we need a photo detector. So here we need a light source that can input this light signal into the fiber. Once it propagated down to the length of the fiber at the output end, we are going to detect this. So there is the device that is called as the photo detector, that is going to detect the light at the output end. Okay, so we have discussed that the diameter of this core and cladding is very small, in the range of micrometers. So whatever light sources or photo detectors we are going to use in this communication system, they must be compatible with the fiber core. So they must also be and the dimensions in suitable for this optical fiber. So they also must be in the range of micrometers. Okay, so what kind of light source are we going to use? LEDs or laser diodes. Okay, we can use LEDs or laser diodes, which are very small in size, serves as a light sources. Okay. The electrical input signal is in general a digital form. The electric signal is in the digital form. It is converted into an optical signal by varying the current flowing through the light source. Using this light source, the light signal, the electrical signal, which is in the form of light, which is in the form of digital form, the digital form electrical signal will be converted into light signal using this light source by varying the current flowing through this light source. Hence, the intensity of light emitted by the source is modulated with the input signal, and the output will be in the form of light pulses. Okay, so we use these light sources to convert the electrical signal into the light signal. The light pulses constitute the signal that travels through the optical fiber. So whatever audio signal or video signal we have, it is now in the form of digital form of electrical signal. It is in the form of electrical signal in the form of digital form, and this digital form electrical signal is has to be converted into light signal, and for that we can use LEDs or laser diodes. Okay, and the light pulses constitute the signal that travels through the optical fiber. So the signal that is converted from electrical signal to light signal, that will constitute the signal whatever we have given as input, whether it can be audio or video. At the receiver end, semiconductor photodiodes or photodetectors, which are very small in size, are used for detection of light sources. So we have used LEDs or laser diodes to input the light signal into this fiber. The light signal is propagated down through this fiber, and it is detected here by photodiode or photodetector. And this photodetector is going to detect this light, and it is going to convert light signal from light signal into electrical signal. Okay. So the photodetector converts the optical signal into the electrical form. Thus, a basic optical fiber system consists a LED or laser diode, optical fiber cable, and a semiconductor photodiode or photodetectors. Okay, so a optical fiber system basically have three important components. The first one is LED or laser diode. That will convert the electrical signal into the light signal, and then the light signal will propagate through the optical fiber. And once we detect the optical light signal at the output end of the optical fiber, that will be converted again into the electrical signal by a photodiode. So basically, you have LED or laser diode. Then you have second component as optical fiber cable. The third component you have photodetector or photodiode. Photodetector or photodiode. So these are the three important components in optical fiber system, which we can use in communications. Okay. So to discuss about as I mentioned earlier, that when does this total internal reflection occurs? Okay. So that is what we are going to discuss now. And this what is this total internal reflection? Before discussing about these conditions for the total internal reflection, it is better to define or know what is basically this total internal reflection. Yeah. So total internal reflection is a phenomenon in which light is totally reflected from a denser to rarer medium boundary, is known as total internal reflection. Okay. So you have a denser medium and you have a rarer medium. So this, for example, this is N1 and this is N2. N1 is here, if I give the condition N1 greater than N2, so N1 is denser medium and N2 is rarer medium. The phenomenon in which light is totally reflected back into the denser medium, and it is reflected from the boundary, denser to rarer medium boundary, into the denser medium. This is known as total internal reflection. Okay, it is a phenomenon in which light is totally reflected from a denser to rarer medium boundary is known as total internal reflection. Okay, so N1, this you can say this is a denser medium because I have defined N1 is higher refractive index and N2 so is lower refractive index. So this is a rarer medium. So the light that is entered into this media as reflected back at this denser to rarer medium boundary, and this phenomenon is known as total internal reflection. Okay, so what is denser medium and what is rarer medium? A medium having a lower refractive index is said to be a optically rarer medium. Rarer medium means lower refractive index. Lower refractive index, rarer medium. Higher refractive index, denser medium. Okay, so rarer medium is lower refractive index. Lower refractive index is known as rarer medium. Higher refractive index. Higher refractive index is known as denser. When a ray of light passes from a denser medium to a rarer medium, it is bent away from the normal in the rarer medium. Okay, so yeah, so that is what we need this N1 and N2 because there should be a bending of light. When there is a difference between these refractive indices, there will be a bending of light. That is the reason why we are taking the refractive index difference. N1 is greater than N2 so that the light is going to bend. There is going to be a reflection at this boundary, right? Okay, so let us see the conditions for this total internal reflection. We have discussed what is total internal reflection. It is a phenomenon in which light is totally reflected from a denser to rarer medium boundary. And rarer medium means lower refractive index, higher medium means the medium which is going to have higher refractive index is called a denser medium. And yeah, let us look into the conditions for this total internal reflection. Okay, yeah. So there are three conditions here. The first one is theta I is less than theta C. Okay, let us see what is this. What happens to this light when theta is less than theta C? Okay, so now N1 is, we have discussed N1 is higher refractive index and this is called denser medium, and N2 is lower refractive index and this is called rarer medium, right? So this is the boundary between this denser and rarer medium. Okay, so this is the light ray that is having this angle of incidence. So angle of incidence is theta 1. I am defining it as theta 1. So theta 1, okay, when theta 1, you can define theta I as theta 1. Theta 1 is less than the theta C. Okay, so I have a critical angle. For example, I know that there is a critical angle for this. We will derive what is critical angle, but first let me say that this is the theta C. So there is a critical angle, but now the angle of incident theta 1 is less than the critical angle in this case, right? So this is the angle of incident, but this is the critical angle. This is the critical angle and this is the angle of incidence. It is clear that theta I is less than theta C. Okay, theta 1 or theta I, you can say this is theta angle of incidence. It's obvious. Okay, so theta I is less than theta C. When theta is less than theta C, the angle of incidence is less than the critical angle. Part of this light ray refracts into the rarer medium, and there is a part of reflection of this light. So there are two phenomena. One, there is a refraction and there is reflection. Okay, so when theta is less than theta C, there are two things that happen. First, part of light reflects, and other part of the light reflects into denser medium, refracts into rarer medium. Okay, so when theta is less than theta C, the light splits into refracted light and reflected light, both. Now, the second condition. So there is no total internal reflection when theta is less than theta C because there is part of refraction. Okay, now let us take the condition 2, which is theta I is equal to theta C. Now, so theta is actually exactly equal to theta C. This is the condition. So because theta 1 is equal to theta C or theta is equal to theta C, then the light grazes at the interface. Light grazes at the interface and yes, grazes at the interface. There is no total internal reflection even when theta is equal to theta C. Okay. So now the third condition is no total internal reflection. The light grazes at the interface, at the core cladding interface. I can define this as core cladding interface. So the third condition, now in these two conditions, we have seen that there is no total internal reflection. Now there is third condition, which is theta I greater than theta C. Let us see what happens. When theta I is greater than theta C, the angle of incident is, so actually the angle of incident is this. So this is theta C. Sorry, this is theta C. And now angle of incident is this. So theta I is actually greater than theta C in this condition. So in this picture, so when theta I is greater than theta C, there is total internal reflection. So there is no refraction, there is no grazing of light at the interface, right? So when theta I is greater than, there is total internal reflection. Total internal reflection. Okay, so there are three conditions for the angle of incidence and angle of critical angle. When theta I is angle of incidence is less than angle of critical angle, there is refraction and reflection. There is no total internal reflection. When theta is equal to theta C, there is reflection and grazing of the light at the interface. There is no total internal reflection. When theta is greater than theta C, only then there is total internal reflection. So for the light to undergo this total internal reflection in optical fiber, we need the angle of incidence must be greater than critical angle. So what is this critical angle that we are discussing about? Right? It's important that if you do not know what is the critical angle for the launching light, so we will not get this total internal reflection, and hence the light, there is a loss of light signal. Okay, it will be useless. So we need to know what is this angle of incidence. To calculate this critical angle, to calculate this critical angle, we are going to use this Snell's law for this medium, right? So if we apply Snell's law for this, n2 sine theta 2 is equal to n1 sine theta 1. So theta 1 is nothing but theta I here. So theta 1 is nothing but theta I. Okay. So theta r is nothing but theta. So here we have defined theta 2 as theta r, refraction. Theta 2 is nothing but theta r. Okay. So using this refraction, Snell's law for refraction, n2 sine theta 2 is equal to n1 sine theta 1. So theta 1 is angle of incidence and theta 2 is angle of refraction, right? Okay, so as for these three conditions, we know if theta is less than theta I or theta 1 less than theta C, refraction is there. When theta I 1 is equal to theta C, there is grazing of interface, and when theta 1 greater than theta C, only then there is total internal reflection. So using this condition, using this Snell's law for refraction, we are going to derive or obtain the angle of critical angle. So using that equation, n1 sine theta 1 is equal to n2 sine theta 2, we can write this equation as sine theta 2 is equal to n1 by n2 sine theta 1, right? So theta 1 is equal to theta C when angle of incident is equal to critical angle. When theta 1 is equal to theta C, we want, then theta 2 is equal to 90 degrees. It is clear that when theta 1 is equal to theta 2, so this is a critical theta r or theta 2, so this is equal to 90 degrees. It is clear. When angle of incident or theta 1 is equal to theta C, theta 2 or theta r is 90 degrees. So we are going to substitute this. So theta 2 is 90 degrees when theta 1 is replaced by theta C, right? So sine 90 is 1. So n2 is equal to n1 sine theta C, or n2 by n1 is equal to sine theta C, right? So in this equation, sine 90 is 90 degrees is 1. So that is the reason why I get n1 by n2 sine theta C is equal to 1, or n1 sine theta C is equal to n2, or sine theta C is equal to n2 by n1, or theta C is equal to sine inverse n2 by n1. Okay. So if when the rarer medium is air, that means n2 is equal to 1. If I take rarer medium as air, n2 will be 1. So I will get 1 by n1. Or you can keep this as it is. Theta C is sine inverse theta C. The critical angle is sine inverse n2 by n1, where n2 is angular refractive index of rarer medium and n1 is refractive index of denser medium. Okay, so this is how we obtain the equation for the critical angle using Snell's law for refraction, right? The important condition is that when what happens when theta angle of incident is critical angle, when angle of incident is equal to critical angle, then angle of refraction is 90 degrees. Using this condition, we derive or we obtain the angle of critical angle. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.